All right, it's 1 o'clock. It looks like it's a good time to start the lecture. This is a second lecture on differential privacy, CS 291A. It's a graduate level course from the Computer Science Department of UCSB. Thank you all for coming, and thanks all those who are attending on Zoom. For those who are asking questions on Zoom, feel free to just unmute yourself and ask. And if students do not hear about what you're saying, I'll just repeat the question so it's clear. So first of all, can you guys all see the shared screen, and can you guys hear what I'm saying? Great. All right, let's get it started. So today we're gonna start to talk about differential privacy, which is the topic of this course. So in the last lecture, we spent some time talking about the challenges of privacy in the big data era, and when all the auxiliary data about individuals are available all over internet, and we talk about some of the subtleties in existing like anonymization techniques that tries to publish a data set themselves by removing the personal identifiable information. And what we discovered is that even if we review only the aggregate statistics about individuals, then those statistics, if we combine them with appropriate site information, they reveal highly sensitive information about individuals. And even for the machine learning models that we train based on a private data set, and those could essentially memorize everything and with all the gory details about individual data sets. And it's opaque, but provided that we know what to ask the machine learning model to predict, it could potentially give us back the information on the individual level. Towards the second half of the last lecture, we talked about a concrete mathematical model and corresponding data reconstruction attack due to determinism. And the gist of this attack is that it's about a fundamental principle of information recovery. So basically, for any algorithm, so if this algorithm is revealing too much information too accurately about the data set, and then it will inevitably lead to a pretty spectacular form of privacy breach. So effectively, using this attack, for any answers about the data set that can be provided, say up to a certain alpha error, and one can make use of these to reconstruct like the 90% of the data set. Okay, so that was the last lecture. So in this lecture, we're gonna be starting to talk about formalizing the idea of privacy. So we'll go over the definition of differential privacy. We'll talk about how we make use of this. So this is really the underlying motivation, and how we use the notion of differential privacy to come up with ways that we can conduct private data analysis. So we will be able to review information about the data while ensuring a very strong notion of privacy for the individuals. So that will be the first half of today's lecture. And in the second half, we'll be talking about two specific ways of achieving differential privacy. One is something that we talked very briefly about towards the end of the last lecture, called randomized response. So it's a really old idea from the 1960s. And the Laplace mechanism, which is one of the most basic mechanisms for differential privacy. Okay, and finally, once we introduce this mechanism, we'll try applying this mechanism to the problem that we set up in the previous lecture on releasing linear queries of an abstract data set that consists of just a bit sequence. Okay, so that's a plan for today. The lecture is based on materials from our textbook. Cynthia Dwork and Aaron Roth, the algorithmic foundation on differential privacy. So the first couple of chapters are really well written. So I encourage you to read chapter 1, chapter 2, and this lecture will be based on chapter 2 and chapter 3.1 to 3.3. Okay, and there are a couple of other supplementary readings for, say, understanding differential privacy on a non-technical level, which helps like us, like once you have taken this course, to explain the idea to people who do not have the same technical ability as you do, and to tell them what this notion of privacy is about and what does it cover. So it's a very good reference there. And very briefly, we'll also be talking about various interpretations of differential privacy guarantees and understanding in what sense it is providing a very strong notion of privacy that is robust and future-proof. Yeah, so we'll cover a little bit of these supplementary material, supplementary reading into this lecture as well. So we'll start with a question that how do we formally define privacy? So in the last lecture, we've seen like various forms of attacks in terms of blatant reconstruction of the data set from the linear thing. We've seen the IMDb the data set being used as a site information so that we can try to link individual data points in the Netflix data set, which is anonymized, to the public data set IMDb's profile by just looking at which movies these people have watched and the extent to which they like those movies. In addition, like we've seen the two attacks on trained machine learning models based on membership inference attacks and unintended memorization, and the list could go on and on and on. And there are many other attacks that we haven't covered, and there are many other attacks that people do not even know is feasible based on the state of the art. So there are attacks in the future, and it is like really insufficient to come up with a protection on a per attack basis. Right, so this is a philosophical question, right? So once there's an attack, we can come up with a defense against that attack. But this defense might not be robust in the sense that there might be another attack that is made possible because of your defense against this specific attack. And if that's the case, and it becomes endless circles, and you go back and forth without finding a satisfactory solution in the end, and the whole procedure, the whole iterations back and forth of defense and attack might not even converge to anywhere that is an equilibrium. So we really need to come up with like for any formal definition of privacy that is supposed to protect against like all kinds of at least a continuous family of attacks. And to achieve that, we borrow some idea from cryptography, which starts the research by first defining a technical notion of, say, indistinguishability or privacy, and then starting from there, we can separate the philosophical discussion of what is the right mathematical definition to how do we come up with an algorithm to achieve these pre-specified definition. And on the definition level alone, even without talking about which algorithm to use, there could be implications of these definitions that imply like natural mitigations of these attacks and many other attacks that haven't been invented yet at this point of time. Okay, so k-anonymity is one of the first things that researchers came up with along this line of putting down like a formal definition about the process or about the output of the private computation, and then like an algorithm or an output algorithm satisfy k-anonymity, or to say it is k-anonymous, effectively says that like there's a data set, and this data set is about individuals and their like various attributes. And if you separate the attributes into one part that is non-sensitive and the other part that is sensitive, so in this case, the non-sensitive attributes are, say, zip code, age, and nationality, and sensitive condition is the disease this person has when they visit like hospital A and hospital B. Right, so let's take a closer look at this example. So there are two hypothetical hospitals where people can visit, and the both hospitals try to come up with approaches that satisfy so-called k-anonymity. which group individuals according to their non-sensitive attribute and do some pre-processing of the data so that every being of this non-sensitive attribute has to fall into has to contain at least k individuals. So on the left, this table is published with 4 anonymity, with k equals to 4. So the typical approaches to achieve this is to use intervals instead of exact values. For instance, these people's age might be 28, 27, 25, but then like we categorize them into the same being of smaller than 30. Right. So in this way, by enumerating all possibilities of zip code, age, and nationality, we can see that this is the first group. This is the second group. They differ only by the interval of the ages, and so on. By doing this, we can clearly tell that this is for anonymous. Similarly, like another hospital in town decide to publish a 6 anonymous version of their data table. Okay, so this is a 6 anonymous, and there are just 2 groups, and each group contain 6 people. But I argue that even though each table on their own is somewhat meaningful for the protection of privacy, at least it satisfies the formal definition of K anonymity. But when we put these 2 tables together and combine them with some seemingly quite benign site information, let's say that there's this person, Alice, who lives in this town. And Alice happens to visit both hospitals. And Alice's boss knows she's 28. And he also knows that she lives in zip code 13012. Okay, so what does it say about her data when her boss happens to look at these 2 already published data table that are 4 anonymous and 6 anonymous? Like her boss can just go over individual entries and see which being Alice is in. So it is clear that Alice is in the first being in hospital A, and also in the first being in hospital B. But when her boss inspect the sensitive condition, you can see that the only sensitive condition that overlaps is AIDS. So this reveals information by just combining 2 K anonymous output, and then suddenly it becomes like not anonymous at all. And yeah, I argue that this is a good example because these site informations are really somewhat benign that you expect your boss would know. Okay, K anonymity was proposed to somehow nullify the data linkage attack because when you try connecting another data set to this data set and to identify individuals, you can only identify that beings of size K. But when you try composing 2 different outputs as K anonymous, and things start to break down. Okay, so then back to the question of how do we define privacy? I argue that any reasonable definition of privacy needs to satisfy these criteria. It needs to protect most of the attacks that are known today. And we shouldn't be making strong assumptions about what adversary should know and could know about individuals. And we shouldn't be making any strong assumptions about what the input data is like, right? So that the kind of protection is universal and it's vitally applicable. And in addition, for the kind of problems that we've seen previously, when the same person can appear in multiple data sets, and the same person can be involved in multiple like publishing of sensitive information from either the same data set or 2 different data sets. And the kind of privacy guarantees, like you should get, like as you publish more information, your privacy guarantee should get weaker and weaker. But we hope that it's not like going from like perfect privacy to 0 privacy with just composing one for once. We hope the degradation of the kind of privacy loss is graceful. As it gradually gets closer and closer to the kind of blatant non-privacy that we've seen in the previous lecture. Okay, so let me talk about the high-level ideas of differential privacy. and how it somehow addresses the desiderata that we covered in the last slide. So the idea of differential privacy is to impose a kind of indistinguishability of two parallel worlds, and these two parallel worlds are world one. This is when Alice is part of the data set, and a parallel world when Alice is replaced by Bob, or Alice is simply dropped from the data set. Okay, so in either of these two worlds, suppose there is an algorithm or some kind of data analysis pipeline that we use to process the data, and the output needs to be randomized, needs to be some kind of a distribution. And what differential privacy requires is that when an adversary looks at a sample from this distribution, when the adversary looks at the outcome of this data analysis, and it is impossible for this adversary to make statistical inferences about whether it was Alice or Bob, or to tell the two different worlds apart. Okay, so these two different words are somewhat similar to each other, right? So they are the same almost everywhere, except for one bit of information where whether it is Alice or it is Bob that is part of the data set that's being processed, right? So it is like, chances are it is like sometimes possible to design such algorithms that are sufficiently randomized such that it becomes difficult for anyone with any information to distinguish between these two. So I'll get a little bit more formal as we write down the formal mathematical definition of differential privacy. But that's the underlying idea. And the logic goes that suppose the adversary cannot even distinguish between the two worlds and cannot even distinguish whether you will be in the data set or not at all, then that means that like the kind of harm that you would incur from this data analysis is limited to the outcome of the data analysis itself, rather than the kind of your action to participate in this data analysis. Okay, so if the attackers cannot distinguish you between the world where you are in the data set or you are not in the data set, then with like any other auxiliary data set that's available to this adversary, he or she cannot make use of it to like improve his or her inference about your existence in this data set at all. Yes, go ahead.
Typically in cryptography, the adversary is also allowed to ask questions to each of these to distinguish these worlds. So what questions are the adversary allowed to ask here?
Yeah, the adversary can ask, say, it will be clear in one of the slides in the subsequently, but I guess this adversary can ask this data analysis platform to return things about this particular data set, right? And these answers that this data analysis algorithm would provide to the adversary will have to be somehow randomized. It will have to be sufficiently randomized so that the two distributions are more or less overlapping with each other with some subtle differences. So at the end of the day, the adversary only sees samples from these distributions. Therefore, information theoretically, you cannot tell whether it is distribution A or distribution B, right? So that's the same notion of indistinguishability from cryptography. Yes, go ahead.
What if the adversary run the queries many times for both scenarios, that Alice is in the data set or not, then the Alice is not in the data set, and compares the average of them together? Yes,
yeah, excellent question. This goes back to the fundamental principle of information recovery. So if all those answers are asked and it requires us to provide accurate answers, so there are like a particular set of questions that the adversary can ask that will result in a reconstruction of the data set. Right, so there's a trade-off between accuracy and privacy, and the goal of differential privacy is to give you something in between and to defer, I guess in some sense to delay the inevitable like eventual outcome that the information will be known in a blatant fashion.
I mean, if we choose the noise from the distribution, not loss or anything, the average would be the same during a long period of time or after many queries.
I mean, if you ask the same query again and again and again, the average, right? Then the privacy, and if you draw independent noise, then you can average it, and eventually you will converge to the mean, right? So that reveals more exact information, and what the kind of gradual degradation of composition talks exactly about this. So as you compose with over multiple queries, then your privacy protection is also getting weaker and weaker and weaker. But it's something that we can quantify very precisely, like how much the degradation is.
So can we change the method for choosing the noise after several attempts for running the query?
Yeah, you can certainly design algorithms to change the noise and increase the noise and use correlated noise. And some of those algorithm design ideas will be covered in this course. All right. Yeah, great questions so far. Yeah, hope the intuition is clear. So I wanted to highlight a subtle difference from the definition of k-anonymity. So k-anonymity is a definition that covers the property of the output. And it doesn't say anything about how you obtain those outputs. So there are various algorithms. So some are randomized and others are not. It's those that are not randomized that are easier to attack because it gives away exact information. On the other hand, differential privacy is a property of the algorithm rather than the output. It doesn't specify what the output could be, but no matter what the output is, it is the algorithm that needs to satisfy differential privacy. Therefore, the guarantee would cover any possible input to those algorithms and any possible output that comes out of those algorithms. So in some sense, we're imposing a constraint on the process rather than on the outcome of the data analysis. Question?
Will the randomization decrease the usability, or does it or is it fine to have
Yeah, the question is that will the randomization decrease the usability or utility of the data analysis? The short answer is yes, but the long answer is yes. Though sometimes you can show that you can still get highly useful results in many cases, and sometimes privacy when you can come for free. So when you compare the kind of additional error that you inject with the statistical error that you have to incur anyhow when your data set is sampled from some population, and the error that's coming from privacy is often negligible. Okay, so we'll get there actually in today's lecture. Yeah, great question. All right, so before we specify the definition of differential privacy, let's talk about the schematic of the model or the so-called curator model of differential privacy and how different pieces of this model interact with each other. And let's also put on some jargon so that when we talk about these things, we're on the same page and we know exactly what we mean. Okay, so different communities may have different names for these, but yeah, let's make use of these names from the textbook, and I'll explain what they mean, say in statistical literature. All right, so this is a kind of curator model setting for differential privacy. So there's a data set, and we assume there is a trusted curator that has access to the raw data set. And the purpose of this curator is to execute some predefined and completely transparent set of protocols to answer questions from any users who wanted to access to the data, or any adversary from the outside world who want to get certain information from the data. The curator will receive that request and then follow certain protocol to come up with answers to address those say SQL requests as accurately as possible. So that's trusted curator. And what is a query? So a query can be, say, a linear query. So I just want to calculate the average of the average income of these individuals in the data set. I want to calculate the variance of the letter grades that a large undergraduate class of students got in the introduction to programming. And those are the query. And the privacy mechanism is a kind of protocol, a predefined protocol, and this algorithm that this curator would carry out, right? So the adversary would send, say, a query, and the curator is supposed to take the data and compute the answer, randomize it slightly, and follow the privacy mechanism and provide an answer to the adversary. And that action of releasing any bit of information from the data following a particular mechanism is called the release. So when I say release, I'm reviewing this output of this computation to the outside world, and I don't constrain who can see this output and who cannot. So that includes any individuals with a huge amount of site information would who may or may not play by the rules that I set in this game, right? So I essentially wanted to sanitize everything that I review to the outside world. There are like, I hope this setting is clear. There are various different mode of operations for this curator. So it can be interactive or non-interactive, right? So interactive queries means the following. Adversary asks Q1 and receives A1. Right, and then after receiving A1, right, so your choice of this Q2 can be a function of can be a function of the previous question and previous answer. Okay, and then based on this the previous transcript, so at the case step, so QK can be a function of Q1 A1, Q2 A2, to QK minus 1 A K minus 1, right? So the point is that in the interactive setting, this is an online rollout of the sequence, and in the non-interactive setting, so all the bag of Q, so the bag of queries is available. So Q is in some predefined queue. This is the offline or non-interactive case. Yeah, so the distinction of these two settings of query release like will be made clear when we get to that part of the lecture. But yeah, it should be clear that if you are able to ask questions based on what the answer you receive, then the search space of the in all the possible queries that you could ask could be exponentially larger. There are other like more complex kind of queries. You can think about this as just a single non-interactive query. For instance, the adversary might be asking the curators to come up with a synthetic data that represents the original data. And the curator would receive that like more complex query and then provide an answer which contains like a synthetic data set that is as large as the original data set alone. And after that, the adversary can make use of the synthetic data set to do anything he or she likes. Like training machine learning models can also be viewed as just one round of this interaction. When Q is to train linear regression model for me, train this multi-layer perceptron for me, and the answers will be returned to the adversary that represent the parameters of the model, or like some predictive function of the model that you can deploy in as a web service. Now, like the next thing that I want to say about this model is that even though we're calling this person the adversary, this person may or may not have like may or may not be ill intended. So this adversary can be your fellow scientists, or it could be just readers of the published aggregate statistics, readers of the journal articles, and this could be, say, your legitimate user of your company's product. Right, so we are calling them adversary because we are not restricting access to whatever that we release. Therefore, it is a conservative view of the world. Like we typically do not make much assumptions about the adversary, but it is sometimes a good idea to think about. Suppose we make what assumptions and whether there are improvements that we can get from the type of algorithms that we obtain. Yeah, for now, like we'll go with a fully worst case sense and consider the adversary to be anyone and anybody who may or may not be have good intention. Okay, I'm gonna define like a few more mathematical notations, which is useful for us to formally write down the definition of differential privacy. So first of all, there is a space of the output for any query that we ask for. Let's say that we ask the curator to train a machine learning model for us. The output space will be the space of all machine learning models. Suppose we ask the curator to say return the aggregate statistics. So how many people in the class likes Justin Bieber? Then the output space will be the space of all integers, all non-negative integers, right? So there's some kind of output space. Let's call that let's call that say B. And then we need to define probability on this output space. Say if B is discrete, then it suffices for us to just define the probability simplex defined on B, which is denoted by this triangle. This is delta of B. So this is a probability simplex, which every element of this probability simplex is a probability distribution that's supported on the output space. Okay, more generally, like you can define any output space as long as there's a valid sigma algebra that you can define. And for the purpose of this course, we are just considering counting measures and Lebesgue measures mostly. And if the output space is discrete, then we're doing counting measure. And if the output space is say R to the D, then we're just using the natural Lebesgue measure for it. Yeah, this allows us to define probability distributions and for us to define randomized algorithm. And what is a randomized algorithm? A randomized algorithm is a mapping. So let's say we call this M, a mapping from the data space to the a probability distribution defined on the output space. And sometimes we call this range of M. So this is all possible output that this M can the space of all possible output that M can produce. And we say that M on a particular data X, then this is a random variable, which says that I'm sampling the output. Like in this tilde notation, I'm calling this draw, like draw or sample from a particular distribution. So more formally, this means that this y equal to m of x is a random variable that has a distribution of m of x. So I'm abusing the little notation a little bit. So this m bracket x represents both a random variable and the distribution of this random variable. All right, so that's what we mean by randomized algorithm, which takes a input data set and it outputs a sample from the probability distribution that's defined on the output space. Now, a little bit more interestingly, how do we represent the data formally? So in the textbook, the data set is represented by so first of all, there's a data space. So I'll first write down the abstract thing, and then I'll explain with a concrete example. So we'll call this calligraphic X to be the data space. With this data space, then any individuals is an element in this data space. Okay, so individuals. Individuals say individual I is in this data space, and this data space can be anything, and it can be discrete. For now, we should just think about this as discrete, and then like the kind of representation that the textbook is using to represent the data set is a vector. A data set is a vector that's in the natural number to the power of the output space, right? So this is the so-called histogram representation of the data set. Let me give you a concrete example. So let's say that this let's say that this data space is the space of fruits. So it is apple, orange, and pear. Okay, and now like we have a data set in our like naive representation that comes as a tuple of n items, and let's say that this data set is apple, pear, apple, orange, right? So this is the data set with 4 elements in it. And how do we represent this data set in this space? It effectively gives us this X represent or histogram representation of this data set would be 2, 1, and 1, right? So this is in the space of natural number to the power of the data space. The data space has size 3, and this list of numbers measures there are 2 apples in the data set, 1 pear in the data set, and 1 orange in the data set. Right? By this representation, we can easily talk about the adding and removing of individuals and its consequences in this histogram. So it's basically going to change the L1, change any of these elements by either adding 1 or removing 1. Yeah, we'll get to the neighboring relationship using this representation in the next slide. And the next thing that I want to talk about is that there is actually a distinction between the individuals and the data of a particular individual. So let's now take an alternative view of the data set. Let's consider that there is a data space which I call X tutor, and this X tutor is the enumeration of all the individual human beings on Earth. Okay, so this is a discrete set, and every say your identification number or your name and birthday and so on. So a lot of these together would provide this like unique identifier of 1, 2, 3, all the way to n, right? So there are n people on Earth, and this is a space of all individual subjects. So what I'm driving at is that there is a distinction between the individuals and how we identify these individuals and the corresponding data of this individual as we collect as part of this data set. So this particular data set about apple, pear, and oranges, they can be outcome of a questionnaire of what is your favorite fruit. Yeah, and any individual here can give me answers. So I might get that the first answer is coming from individual 56, and the second answer is the individual 78. Then fourth answer is 101, and the last answer is 111 1001. Okay, so these identifiers are not made explicit in the tuple representation of this data set, nor is it like relevant for this histogram representation of the data set. But on the other hand, like on this space X tutor, there's an alternative histogram representation that we can talk about that's completely independent to this histogram or this tuple representation of the data set. So this is alternative alternative representation of the individuals. Yeah, so this will be also a long bit vector where the 56 is given by 1, and then the 78 is given by it has a 1, and everything else has 0, 101 and 1001. Yeah, so this will be a bit vector of either 0 or 1 in the space of X tutor. Okay, so I argue that for this version of the data set, you could also say like use the same kind of L1 metric to determine the adding or removing of individual. Suppose we add 1 individual, so one of these 0 will be toggled from 0 to 1, and suppose we subtract 1 individual, then any of those ones, some of those ones will be toggled to 0. Okay, so that's two ways that we're going to be representing the data. Actually, three ways that we're going to be representing the data. The histogram of the data of individuals, which can have like multiple people mapping to the same element in the data space. The histogram of individual identifiers, which is a long vector that enumerates all individuals in the entire world. And every element of this vector needs to be binary in value. So you are either in the data set or not in the data set. And there shouldn't be like two individuals with the same identifier. And the third version of the data set is a kind of a multi-set representation of the data set, or this tuple representation of the data set. Is a typical kind of data set that if you do data science and statistics, you will see, then every individual is represented by a row of attributes. And these attributes, so this is a data matrix representation. And every row is an individual, and it talks about your age, your gender, your preferences of the fruits and so on. And those are information and what we call the data point of an individual. Yeah, I hope clarifying like these subtle differences between different ways of representing the data set will make it clearer in the remainder of the course. Yeah, a little bit more mathematical notations. So now that we have a representation of the data set, we can talk about the distance between two data sets. For any of the histogram representation, for either of the histogram representation, we can simply use the L1 distance this is equal to a sum over I from 1 to say capital S, xi minus yi absolute value. So it is a standard definition of the L1 distance of the two vectors, and this measures the number of people you need to add or remove to go from X to Y, to go from data set X to data set Y, right? So X, Y, they are both in, say, natural number to the power of data space. Okay, and the same thing, the L1 distance can be used to define the distance between two data sets in this identifier indicator vector. Now, the next thing that we're going to talk about is the neighboring relationship. So recall that differential privacy requires us to define two parallel worlds that are subtly different from each other. So the version that we showed is that we can replace Alice with Bob in an alternative world. So that's not the only way of defining neighboring relationship. And that particular version is called replace. Replace one. A neighboring relationship, which means by swapping one individual with an arbitrary another individual. And the more general and more commonly used neighboring relationship is the so-called add or remove version of the neighboring relationship. And this neighboring relationship says that two neighboring data set is defined by, say, data set X is neighboring, is a neighbor of Y if and only if the L1 distance of X and Y is smaller than 1. Okay, I hope that definition is clear. Now, with that set, we can talk about the formal definition of differential privacy eventually. So this is definition 2.4 in Dwork and Roth. So we say that a randomized algorithm M is epsilon delta differentially private. Is epsilon delta differentially private if for any measurable set of the output space, and for any neighboring data set X and Y, the following inequality is true. I highlight for all neighboring pair and for all possible output, a set of output of this algorithm, it needs to satisfy that the probability of seeing this particular output, is bounded by the probability, like in one data set X, it's bounded by e to the power of epsilon multiplied with the probability of seeing the same output when the data set is changed into this neighboring data set, plus and some like small probability delta that we add to this. And this probability distribution is entirely determined by our synthetically generated distribution from the mechanism itself. So in statistics, typically we assume some kind of data generating distribution, and in machine learning, we assume the data set are drawn IID from some unknown distribution. None of that is happening here, and this probability is only due to the random coins that we toss in implementing this randomized mechanism M. And we call this epsilon delta dp, and if delta is 0, we say that M is epsilon pure differentially private, or pure DP. Like two more remarks. We can define the neighboring relationships differently. So over here, we're defining the neighboring relationship by this L1 metric in a histogram representation of the data. We could define it in other ways. We can define the data space in a slightly different way. For instance, like just now, like suppose the data matrix space, let's say the data space is X. So the data matrix space can be the space of empty set union with the number of data points in this data set from 1 to positive infinity and X to the power of n. So this is a set of the set of all data sets with an unspecified size, right? So any data matrix is part of this space, and then we can define either adding or removing individuals, or we can define replacing individuals while they remain within this data space. So for any valid neighboring relationships, that we can define the differential privacy, and that talks about the so-called granularity of the privacy protection. So if you add or remove an entire household and define that as a neighboring relationship, then the kind of DP guarantee would apply to your entire household rather than applying to just one individual in the household. If you add or remove an entire participation of like a smart device in the federated learning setting and do that differentially privately, and define that as a neighboring relationship, then you are protecting that whole smartphone. And you could say that multiple smart devices can belong to the same person, and then you can add or remove that individual person. So there are some flexibility there for different use cases when you make this definition. And again, like I've already highlighted this for all S and for all neighboring X and Y, and this inequality needs to hold for any pair of neighboring input. Okay, and when delta is 0, this is equivalent to when delta is 0. This is equivalent to the log of probability ratio being smaller than e to the power of epsilon. Okay, and a quick question here, like why don't we need the why don't we need absolute value here? The log odds ratio is something that's coming from Neyman-Pearson lemma, which says that to test the 2-point hypothesis, and this is like really the right statistics to compute, and it suffices to threshold these statistics, and that gives you the uniform most powerful test, the best classifier in the entire universe. But thresholding this like typically requires you to threshold this absolute value at some location. So why don't you need like in this definition, to have an absolute value here? Why don't we need this inequality to hold on both directions rather than just one direction? Anyone? Yeah, exactly. Yeah, since we're enumerating over all neighboring pair of X and Y, and this relationship is symmetric. If you are my neighbor, I'm your neighbor too. So it is already encoded in this for all X and Y, such that we don't need to redundantly add the absolute value or specifying the two-sided inequality like anymore. And this is just slightly shorter representation. Yes.
I just don't understand. So if we just left the epsilon to be a little bit loose, would I still need delta?
Well, yeah, I'll talk about epsilon and delta. In the
And also the thing is that for the L1 distance between the two major data sets, you need to have a specific question like what is the favorite fruit, and then you have this histogram. But if you have a different question, then wouldn't that be different?
Well, like the data of the data point representation of each individuals is described by this data space calligraphic X, right? So the example that I gave is a simple example when this calligraphic X has just three elements in it. On the other hand, it can be more complicated. It can be, say, a d-dimensional real value numbers that describe your biometric, your DNA sequence, and so on. So it can be more complicated, and depending on what your application is, the space of the data is clearly have to be different.
The upper bound shouldn't have the E, right?
Should have a what?
So on the right hand side, the upper bound of the log.
Oh, yeah. Thank you for catching that. This is a typo. Since I've already taken log here, so this is just epsilon. All right, so let me explain this a little bit more graphically. So for all, like, let's say that these are the red and blue are the two distributions that are coming from the mx and my. Now, what does this S mean? This means that, say, some region of this output space. So this is S, region of the output space. And what the definition says is that for any such output space, and the area under the curve of the blue and the area under the curve of the red, they are related by a multiplicative constant and also by an additive constant. So for now, let's ignore delta and take delta to be 0. So in this case, we want a universal multiplicative approximation of one world using the other world. So even if this S happens in the tail of the distribution, even if this happens here, and we still, even if this individual X event happens with tiny probability, then we still require the multiplicative approximation of the world, right? So it's a very strong notion of protection. And now let me interpret what this delta means. So it basically says that when this event S happens with a small probability, happens with a probability smaller than delta, under the first data set, then I don't really care whether this will happen at all, whether the multiplicative approximation is valid. So effectively, by choosing delta to be larger than 0, then we are more permitting, and we're allowing us to ignore like some small probability event that will happen. And when those events happen, then we don't really need to worry about privacy. And it's mitigated by the fact that those events do not really happen very often. Okay, so I hope this is clear. And this S can be arbitrary, right? So we can take union of different beings. And one additional remark is that when both M of X and M of Y, when both of them has a probability density, then it suffices to bound the log density ratio for every possible input to that log density ratio. Because if you can bound like for every point, then that implies the integral is also bounded. Yeah, in terms of the probability mass. All right, so we'll focus on just pure differential privacy for the first few lectures before we talk about what happens when delta is small. There are some reasonable ranges for these privacy parameters, epsilon and delta. So yeah, epsilon and delta are called privacy parameters, and they measure the loss of privacy. So epsilon, e to the power of epsilon is a multiplicative approximation. And we want epsilon to be very small. And let's say that when epsilon is close to 0, then e to the power of epsilon is close to 1. Then this is saying that we get a strong multiplicative neighboring multiplicative guarantee on relationship between the two neighboring data set on any event. And the commonly accepted choices of these privacy parameters are epsilon is say a small constant. Typically, it requires we require epsilon to be smaller than 1. But yes, like any like small constant is reasonable. When it is smaller than 1, then the privacy guarantee is slightly stronger. And delta is required to be very small. Sometimes we want it to be cryptographically small in the sense that asymptotically, as the size of the data set goes to infinity, and then the decay rate of delta should be faster than any polynomial, but possibly slower than an exponential function. In practice, however, choosing delta to be this small is very harmful in terms of the utilities that you will get. So in practice, people typically choose anything that's smaller than this is little o, like goes to 0 faster than 1/n. For instance, choose delta to be 1/n squared is a safe choice, like the empirical evaluation of your methods in practice. So I want to just mention that why it is not okay to choose delta to be, say, larger than 1/n. So one typical example that people give to illustrate is that 0 delta or 0 1/n dp guarantee is somewhat meaningless because they are like instances of mechanism that actually violates your privacy quite badly. So take this mechanism, for example. Now you have a data set of n individuals. You randomly output I and the data associated with I. With I drawn from uniform 1 to n. Right? So it's not hard to see that this algorithm actually satisfies 0 1/n dp, because for any neighboring data set that differs by just one individual, right? So the probability of this algorithm outputting that individual is 1/n, right? So this is 0 1/n dp. But on the other hand, it also has a bad implication that there is always going to be some unlucky person whose raw data is explicitly revealed together with his or her identifier. Okay, is that yeah, I hope that's clear. Right. So far we've talked about the definition of differential privacy, and like we made a claim earlier that DP is resistant or robust against any kind of side information from the attacker, from the adversary. So there is a interpretation of this through a Bayesian, like almost equivalent definition of differential privacy, which comes from like this paper on the semantics of differential privacy. I think it's nice to cover. Let's think about the situation where the adversary has some type of side information that's encoded in a prior belief of anything. Let's say that the adversary has a prior of pi So and this is a prior belief for certain object, and this object can be about the data set, can be about anything in the entire world. And the form of this prior belief, it can also be anything. And so anything that can encode any form of side information that's available to the adversary. What what the adversary will end up doing after receiving so the adversary receives the output say y drawn from the output of the computation. So X is a data set, right? And what the adversary can do is to update the prior into a posterior, right? So m of X is equal to y. Okay, so what the Bayesian interpretation of differential privacy says that if we compare say the total variation distance, so which is the distance of two probability distribution of the two posterior mx equals to y and pi of like the same object that this adversary is making inference on, m of X, say remove Alice, been returning the same output y. So the total variation distance is actually smaller than e to the power of epsilon minus 1. And this holds for any pi, and also holds for any input data and any individuals that you add or remove from this data set. Right. So in this sense, like you can, from a Bayesian perspective, you can encode anything using a prior belief. And what differential privacy protects is that no matter what our prior belief is, it's going to be updated into a posterior belief, and that posterior belief will be like very similar to the posterior beliefs that you will get when you assume the data that's being processed is like that doesn't have this individual, right? So the participation of Alice in the data set like doesn't really affect the ability of the adversary to make inference about anything. But notice that this is anything, not just the inference about whether Alice is in the data set or not, but really like anything in the entire world. Like another way to think about the set information is through a more frequentist way of thinking about the problem. So let's say that the data set, like this is what statisticians typically do. We assume that the data set X is drawn from some distribution, and sometimes every row of this data set is drawn IID from some distribution. This is we call this X. Then like, what does site information help us? Let's say that having a site information aux, having access to this site information allows this adversary to know more about the data set. So yeah, I guess like for someone who do not know the data set, the output of the distribution will be the following. So for first of all, X drawn from D, and secondly, the output Y is drawn from M, given to you by X, right? And then this is a DP data analysis. This is how the data itself is generated. Now let's say that the adversary knows the site information aux, and what this information tells you is that the distribution of X is now updated into the conditional distribution by conditioning on aux, right? And then the whole pipeline will be X. The data set is drawn from this, and well, now it's the same DP mechanism that processes this X. Does this make a difference? So of course it makes a difference on the final distribution of y, because y has y's distribution has a contribution from both the data generating distribution and the part of the distribution that's added by the differential privacy mechanism. But the worst case nature of the DP definition actually prevents this kind of inference based on this auxiliary information from making any difference. So no matter what this aux is, and since DP applies to all possible input data set after the data set is realized, then like no matter what the input distribution of X is, the epsilon DP or epsilon delta DP guarantees will be applicable, like no matter what. Okay, so that's another way of thinking about thinking about site information. So we'll talk about these slides and then we'll go to our break for 5 minutes. So a couple of desirable properties of this differential privacy on the definition level is that first of all, it allows it is close to post-processing. So let me explain what that means. If M is epsilon delta dp, then that implies that for any function f that we process the output of M, this mechanism is also epsilon delta dp for any post-processing function f. So I'm using this this little circle to denote the composition of functions. So f of M is equal to, say, applying f to the output of M. So this is what I mean with this circle. So the proof is actually quite straightforward. First of all, it suffices to just consider deterministic f, because for randomized f, they are like a convex combination of a bunch of possibly infinite number of deterministic f. So it suffices to consider deterministic f. And for deterministic f, and then we should just follow the definition of differential privacy. So this is a probability of f M apply to data set X. This thing, let's say that the output space of F is, so let's say that for any set in the range of F, any set S in the range of F. So this is equal to the probability of Mx being in some T, some set T. And what is T? T can be defined as a pre-image of S. Okay, so what I mean, this is a set of all elements in the output space of M, such that f of T will be inside S. So this is called a pre-image. Okay, now it's clear that with this pre-image definition and this equal is true, and then by applying the definition of M is epsilon delta dp, I can write that this is smaller than e to the power of epsilon probability of M of y inside T plus delta. And then by applying this definition of pre-image again, we can write that this is equal to e to the power of epsilon PR of F M of y inside S plus delta, which checks the definition of differential privacy, which says that any post-processing is okay and it retains the same privacy guarantee. Okay, now composition. Let's say that you have M1, which satisfies epsilon delta dp, and you have M2 that satisfies epsilon delta epsilon 2 delta 2, epsilon 1 delta 1 dp. And what this is saying is that M1 and M2 together applying to the same data set will return an output that is epsilon 1 plus epsilon 2 delta 1 plus delta 2 dp. Yeah, the proof of this is slightly more complicated when we allow delta to be larger than 0. So let's prove this for the case when delta 1 and delta 2 is equal to 0. Yeah, let's prove this special case. So again, it can be proven by just following the definition. So for any output space S1 and S2, So the probability of M1 X and M2 X belonging to S1 cross S2, and since these two are conducted independently, so let's maybe consider adaptive composition. Adaptive conformation means that the choice of M2 can be a function of the output of M1. So by the factorization of the distribution, we can factorize this into M1 of X belonging to S1, and now then the probability of M2 of X belonging to S2 condition on the output of M1 of X. Yeah, so and the sum over all possible S in S1. Right. So by just decomposing this joint distribution into the into the factorized distribution, and we can just write this into the probability distribution of this individual mechanism. And then since M2 is differentially private for any like possible choice of the M1's output, then we can bound the second part. We can bound the second part with e to the power of epsilon PR of M2 Y belonging to S2 given M1S. And then we can like then for this one, we can also bound this one to be smaller than e to the power of this is epsilon 2, and this is e to the power of epsilon 1. PR of M1 Y is equal to like the little the little s, and once we do this, the whole thing becomes sum of S in S1. And let's group this e to the power of epsilon 1 and e to the power of epsilon 2 together and extract it out in the outside. You will have e to the power of epsilon 1 plus epsilon 2, and then PR of M1 Y equal to S. So this is really the density function, and the probability of M2 Y belonging to S2 given M1 S, which like M2 is adaptively chosen in this interactive setting. And the right hand side is precisely e to the power of epsilon 1 plus epsilon 2, the probability distribution of seeing seeing the same output when the data set is Y belonging to S1 S2 set. Okay, that's a proof for the adaptive composition or interactive composition. I hope the argument is clear. And then lastly, DP doesn't just cover individuals with one single granularity. So in some sense, the same algorithm and the same definition would automatically apply to a household of 3 people and a university of 100 students as a whole. But the kind of privacy parameters would get worse again, like gracefully. So this is what we call the small group privacy. So if M is epsilon dp on say add or remove one person, then M is also like K times epsilon dp on adding or removing any group of K people. Yeah, so the proof is pretty simple. It checks the definition of the pure DP, and I leave it as an exercise. And the version of the small group privacy for epsilon delta DP is a lot more complicated. Okay, yeah, we'll take a break and we'll resume the lecture at 2:19. then it covers all n at the same time. Then the mechanism should be able to take a input of a data set of arbitrary size n. Then in that case, it's a better idea to treat this delta as a function of a sensitive information n, right? So in that case, n is actually a sensitive information, right? So knowing n or not knowing n could reveal individual information.
Yeah, so in here, it means that we saw this delta and epsilon for fixed n.
Right.
So n is the size of x.
N is the size of the data set.
Yes, the data set x.
Right.
Okay.
Yeah, it's just in the same statistical sense. Now, on the other hand, if you consider the symmetric neighboring relationship when you are just swapping or replacing one Alice with Bob, then in this case, the space of the all data set that you can your algorithm can take all have the same n, right? So in this problem, you have a different guarantee for every n separately. Then this becomes, I guess, more well defined. Okay. Great. Yeah. Well, welcome back to the lecture. So let's. Yeah. So this is where we stopped. So we talk about the desirable properties of DP in terms of its composition, closure to post-processing and the small group privacy. Yeah, there are a few, there just I think 2 more slides about the interpretation of DP. So I wanted to give this example and talk about this very important caveat of differential privacy, because it's easy for people to misunderstand the protection of DP, given that it is so strong to think that it is something that's going to prevent all kinds of harms that's coming from a data analysis. So this is categorically false, a false statement. So the best way to illustrate this is from this example of a medical study. Let's say that we conduct a study differentially privately about whether smoking causes cancer, right? So since differential privacy allows us to do such data analysis with high utility, then it is likely that a sufficiently large scale study like this will establish with statistical significance that smoking is actually causing lung cancer. Now, Alice is a smoker, and because of this study, Alice insurance company who knows the outcome of this research study will increase the premium for all smokers, including Alice. And since Alice participated in this study and she also receives this harm in terms of her insurance premium increased. Does this break DP? Is a question. Yeah, I heard one answer, no. Could you elaborate a little bit?
I think if Alice isn't in this data set, the study will get the same result. So it's the same. So if Alice isn't in this data set, her insurance company will still increase the premium for her.
Yeah, exactly. Yeah, that's exactly the reason why this is a kind of harm. It's a concrete harm that could happen to Alice. Yeah, by the way, I should have repeat the answer. So the answer from Dan is that Alice is a smoker, and this doesn't break DP because whether or not Alice is in the data set or not, the signal is so strong that the study will draw the same conclusion regardless, right? So there is actually a risk that's harms that comes together for Alex due to the conduct of this data analysis, but it is not because Alice's participation in the study. And whether or not Alice participates in this study at all, in the 2 parallel world, it is still indistinguishable. But regardless of which world that we're in, the outcome will be that the Alice insurance premium will increase. Right, so it doesn't break DP, and this is actually the intended use case for DP. So we shouldn't think of DP as something that's a silver bullet that prevents all kinds of harms. And then in this case, a harm, these harms are effectively encoded in the utility of the data analysis itself. So any procedure that allows this data analysis to be conducted with high utility will have to incur such a cost. And it's not something that any algorithm or any mechanism could have prevented. Okay, and so it will be like a like a social choice question on what are the kind of study and what are the kind of applications that we should run at all. And the only way to prevent this kind of harm from happening to individuals is to prevent science from happening, which may or may not be a good idea to argue strongly against. Okay, so let me summarize. So there's a particular promise that differential privacy as a definition is making. So first of all, it instead of nullifying all privacy risks to individuals, differential privacy allows us to decouple the risk of the study itself and the risk of participation in this study. So in this way, from an economic point of view, like we only need to provide a little bit of incentive for people to actually participate and make the science happen. Secondly, like we should think about DP guarantee as a relative guarantee, and privacy loss epsilon is in some sense a risk multiplier. So recall the definition says that the probability of any S, M of X in any S is smaller than e to the power of the same S happening if the data set is from the world that's without you participating. And this e to the power of epsilon is what we call a risk multiplier. If by not participating or by participating, there are certain risks that's going to incur to you, like with this probability, and then the differential privacy is a relative guarantee that says that this trick is only going to get e to the power of epsilon a factor larger. So DP aims at hiding or restricting access to the information specific to individuals, but still somehow permits information about the general population and about the distribution to be learned accurately. If we think about the goal of statistical inference and machine learning, we're not hoping to actually memorize the data set and to do well on the training data. The end goal of any statistical analysis, statistical inference, and machine learning development is to be able to predict in future data that are not part of the training data, right? So for that goal, the DP and all these like data analysis tasks, their goals are actually well aligned. And DP is one way for us to formally prevent that when you are trying to achieve the goal of generalizing, and DP can be used to limit the unintended harm that incur to individuals in the data set. Okay, so that's the promise of differential privacy. It doesn't promise everything, but it is promising a fair amount that's making the techniques highly useful. Yeah, as a quick checkpoint, these are some of the qualitative properties of differential privacy that after today's lectures you should understand and remember, and you should also read the textbook which articulate many of these points like very carefully in the first 3 chapters. So I'm not gonna read these to you again. Yeah, in the remainder of today's lecture, I think we have 22 minutes. I'll try to cover as much as I can. If I don't finish everything, then we'll just continue on the Monday lecture. So in the remainder of the lecture, we'll talk about like 2 concrete mechanisms: the randomized response, the Laplace mechanism, and then try applying this to answering linear queries that we studied in the first lecture. So let's first revisit randomized response. So this is a mechanism from 1965 by Warner that allows individuals to respond to some sensitive or embarrassing question. And instead of just giving away your question directly, you toss a coin, you toss a biased coin and then answer honestly when it is head. Otherwise, you answer the opposite. Okay, so how do we like how do we mathematically write down this like algorithm? So first of all, what is the output space? The output space is just 0, 1. The randomized response is I guess the input space is 0, 1. The output space is also 0, 1. The randomized response is a randomized procedure that all samples from a distribution that's defined on the probability simplex like of the output space. And what this procedure says is that like maybe we can let's say that the input secret bit is X. Input is X, and the output is a random variable Y, and the randomized response would be like a mapping of Y from X, and then maybe we can calculate the expected value of Y. So expected value of Y given X is equal to 1. So this is equal to, yeah, suppose the true. So let's maybe calculate this. So it's a with probability P, then you get 1, and then with probability 1 minus P, you get 0. So this is P. And what happens if X is equal to 0? So in this case, you got P multiplied with 0 plus 1 minus P multiply 1, then you get 1 minus P. So notice that the expected value of this Y is not really the same about as the actual answer that we want to output. Yeah, we just want to output X, right? But this is giving me something between 0 and 1 rather than at 1 or at 0 in expectation. But what we can do is to somehow make use of this output random variable Y to come up with an estimator of X, right? So let's try come up with X hat so that later we can make use of this to do something useful. Right, so we can construct an estimator. An estimator is a mapping from the data to some other is a function of the data, and then some of the desired property is that this estimator is unbiased in the sense that the expected value of X hat is equal to what we are trying to approximate. And maybe let's try achieving that. Like we can like think about what this estimator is, but just let me write down the answer. So this X hat can be shifted and scaled of the version of this Y. So basically a linear transformation of this Y. So it can be Y minus 0.5 over well, I guess 2 times P over P minus 0.5. Okay, might be unclear like why I'm writing this down, but now let's calculate the conditional expectation of this estimator. So when X is 0, so this is 0.5 plus the expected value of Y given X is 0. So that's 1 minus P minus 0.5 over 2 times P minus 0.5. What is it? It gives me 0, right? And that's what we want. And similarly, E of X hat X equal to 1. You can verify that this gives you like 0.5 plus 1. I guess P minus 0.5 over 2 times P minus 0.5. And it gives me 0.5 plus 0.5 is equal to 1. Right, so X hat is an unbiased estimator. Okay, so the next thing that we want to figure out is whether this algorithm is actually differentially private. Okay, and if so, how is a parameter P like related to how is this parameter P related to the epsilon parameter is in the differential privacy guarantee? Okay. So like in order to formalize that, we need to answer these 3 questions first. So what is the data set, what is the mechanism, and what is the neighboring relationship to define DP? So in this case, the data set is just 1 bit, right? The data set can be either 0 or 1. and it cannot be anything else. So this is just a data set. And what's the mechanism? The mechanism takes the data set and its value and then output a random bit, right? It's the mechanism is like as we specified, is random response specified with a parameter p, which output x with probability p, and 1 minus x with probability 1 minus p. And the only neighboring relationships that make sense for this mechanism for randomized response is a replace one like neighboring relationship, right? So since there are just two elements in the data set, like one is neighboring to the other, right? There is no other way of defining a neighboring relationship. For instance, adding or removing, like it doesn't make sense because we don't really have an empty set in the space of the data set, right? So the neighboring relationship will be the replace one. Now with all these set in stone, we can try to work out the privacy parameters of randomized response. So since this is so simple, we'll just enumerate all these different possibilities. So recall that the DP definition requires that for any pair of neighboring data set, that inequality needs to be true. So in this case, there are just two possibilities. We can choose x to be we can choose x to be 1, y to be 0, or we can choose x to be 0 and y to be 1. So that's the only two possibilities of two neighboring data sets. Okay, so we'll go with the first. And how about the output space? So the output space is also just 0 or 1, right? So remember, it suffices to consider the density ratio. It suffices to enumerate every element of the output space. And then with the sigma algebra, it also covers all possible events. So let's try to work it out. So in this case, the probability, so again, like this RR with parameter P, it takes X and output Y. Okay, so Y is equal to 1, given X equal to 1. So in this case, by the definition of randomized response is equal to P, and let's add multiply, divide and multiply 1 over 1 minus P. Okay, and this is equal to e to the power of log P over 1 minus P, and e log P 1 minus P, probability of Y equals to 1, given X is equal to 0. Okay, because this and that, they are the same. Yeah, so everything is equal, therefore inequality is true. Now let's consider the other possible output. This is equal to 1 minus P, and using the same trick, I can get 1 minus P, divide P and multiply P, and I get e to the power of log 1 minus P over P multiplied by P, and this is e to the power of log 1 minus P over P, and P y equals to 0, X equal to 0. Okay, so we have these exact calculations of these multipliers, so then it suffices for us to take the larger of these two. Which one is larger? The one on top is larger, since we assume P is larger than 0.5, right? So then there are two other cases. The case when we toggle X and Y, when X is equal to 0, Y is equal to 1, and everything is symmetric. So I'm gonna skip that and conclude that epsilon parameter is equal to log P over 1 minus P. And we can make it more explicit by we can just try inverting the equation by exponentiating on both sides and get e to the power of this is equivalent to say e to the power of epsilon is equal to P over 1 minus P, and also the same as saying that the choice of P when we want to satisfy a particular pre-specified privacy budget epsilon, you'll get e to the power of epsilon over e to the power of epsilon plus 1. Now something like a logistic function. All right, so by choosing this parameter P, then it gives us an epsilon DP algorithm, and this altogether implies that RRP is epsilon DP with epsilon equal to log P over 1 minus P. Okay, so the very basic algorithm is indeed pure differentially private, and we've worked it out. The second algorithm, and a very basic algorithm of many like it's a fundamental building block of many more complicated differentially private algorithms, is called Laplace mechanism, and this is also the mechanism that was proposed in the original paper by Dork et al. In this 2016 paper. So it addresses a more general problem of possibly a real valued or a numerical valued output like query. So let's say that the query asks the data curator to come up with the answer to this function, which takes the data set and outputs some real value in R to the K. Okay, so this is like very general kind of a family of queries. And in order for Laplace mechanism to work, we need to define the so-called L1 sensitivity. So L1 sensitivity measures the perturbation of this function f's output when we change the when we change this input from x into a neighboring y. Right, and it is L1 sensitivity because we're measuring like the sensitivity of the output of f by just adding the absolute value differences of the changes. Okay, and this could be replaced with any neighboring other neighboring relationships. Yeah, and this is L1. That's why it's called L1 sensitivity. And how does Laplace mechanism work? It's very straightforward. You simply add noise to the exact computation. So you apply f to this data set, you get some numerical value in R to the K, and then you add IID Laplace noise with this parameter to every coordinates of the output of f. And the choice of the parameter of this Laplace distribution is chosen according to the known sensitivity and your desired privacy parameter. And it can be shown that this algorithm is epsilon dp as well. So let's take a closer look of what Laplace distribution, what the Laplace distribution looks like. So this is like taken from Wikipedia. So you can see that the Laplace distribution is really the double-sided exponential distribution with a probability density function looking like this. So B is a scale parameter of this Laplace distribution. And with a double exponential tail, and when you calculate the normalization constant, you get this 1/2b. Okay, on both sides, it's a pointed distribution, but on the left and on the right, it's an exponential tail. Yeah, so now having a little bit of intuition of what this distribution is, then we can try proving that Laplace mechanism satisfies differential privacy. All right, yeah, I think that's probably the last thing I'm gonna do today. So let's go over the proof of the Laplace mechanism and show that this is differentially private. Yes.
Sorry, I wanted to ask what B in the previous slide was.
Okay. So B in the previous slide was B is chosen to be the L1 sensitivity over your desired epsilon parameter. Yeah. So this is a choice of B. Yeah. Excellent question. All right, so so the output m f of x is just going to be f of x plus z, where z is IID. Okay, for every coordinate. Now we also know that the Laplace distribution has a density p of zi. Is e to the power of minus zi absolute value over b over 2b, and again b is chosen as sensitivity over the privacy parameter. But let's use B and then later plug this back into the calculation. So since both distributions has a density, it suffices to consider it suffices to checking the condition for density. And since we're proving the pure differential privacy, like we can get away with dealing with density alone. So it suffices to show that the P of M, the Laplace mechanism is I guess equal to some value y is smaller than e to the power of epsilon. P of M f y is equal to yeah, I'm using y. Let's use x tilde. Use let's use x prime as the alternative neighboring data set. So now since y is reserved for the particular output of the Laplace mechanism. So this is what we're trying to prove. Okay, we're just gonna prove this by substituting the definition of the density function and using the fact that these are independently drawn for every single coordinate. So let's factorize this. So this is equal to the product of I from 1 to k and e to the power of minus. I'm just substituting the definition of this. Since we're adding this, the mean of the distribution will be f of x. Okay, and the more that you deviate from f of x, then that's absolute value of z, right, over b, and then there's a 2b normalization constant that's outside. And then we can what we can do is to just add and remove these individuals. Add and remove these individual coordinates for those that are coming from f of y, f of x prime. So this is the same as e to the power of minus by minus f of x, absolute value, i's coordinate. So I'm gonna subtract y minus f of x prime, absolute value I. I'm gonna add it back. Okay, and over to B. Now, since this is a product of exponentials, I can put this product into the into the exponent, and it becomes a summation, right? So this is equal to 2b to the power of k and e to the power of minus, I guess sum from I from 1 to k, y minus f x prime, i's coordinates, minus y minus f x, absolute value, i's coordinate. All right, and then there's this additional thing, which is minus, so the minus and plus, again, minus b over y minus f of x prime, absolute value I. Right, so everything over here is on the exponent, and now by triangular inequality and the fact that the exponential function is monotonic, I can upper bound this difference with the so this is smaller than 2b to the k e to the power of I can upper bound this with f x prime minus f of x, absolute value. Okay, I can always do this for each of the coordinates, and minus b of y minus f of x prime I. But this is something that we know, right? So now we are getting the from the triangular inequality, they were getting the sum of the I coordinates from the differences of fx and fx prime. And since we are assuming that the global sensitivity, the sensitivity delta f is the L1 distance of f of x and f of x prime, and the fact that x and x prime, they are neighboring, then I can further bound this with I can further bound this with e to the power of b, like delta of f, and then I can like just rewrite this as minus y minus fx prime I over B, I can like write the summation over here for this quantity. And by our choice of B, then we can already see that when we choose B to be this, then we get e to the power of epsilon. And by grouping the normalization constant with every component of this density function, then we recover the P of MF acting on X prime is equal to Y. And that completes the proof that Laplace mechanism is epsilon differentially private. Okay, that's yeah, that's what I'm gonna cover today. I have a few more slides which I'll continue in the Monday lecture, where we're going to be analyzing the utility of the Laplace mechanism and the utility of the randomized response using that estimator, using that debiased estimator that we've derived. And then we'll come up with interpretations of how we can apply this mechanism to answering like a large bag of linear queries in the setting that we considered in the first lecture. All right, I'll stop here. And thank you all for coming.